Hi, my name is Alex, and today we are going to learn how to use Node.js to verify digital signatures. This lesson is actually based on the article that I wrote and published on medium.com, so you are welcome to go and read this article, and the link is provided behind the video. So, once again, what is the goal of today's lesson? And the goal of today's lesson is to better understand the practical, and I focus again, practical implementation of private public key encryption using Node.js. We are not going to cover theory behind the private public key cryptography here. We are just going to learn how to implement it into using the code using Node.js. So I do assume that you have Node.js already installed, and I also assume that you use some kind of text code editor. I'm using Microsoft Visual Studio Code, but you're welcome to use any editor you like. If you have any troubles of downloading Node.js or installing some code editor, please shoot me questions, ask me questions, and I can help you with the installations. But at the moment, I assume that you have Node.js installed, and I assume that you use some sort of a code editor. So back to the lesson. To better understand how the magic of private public key encryption happens, we're going to the three steps. First, we create private key and associate it with public key. Second, we use private key to digitally sign a message. And third, we see if it really works. We see if the person, the receiver, who can receive some publicly available information can for sure determine if the message was actually signed by the person who owns the private key. Okay, so three major steps, and after that we will hopefully understand the practical implementation of magic of private public key cryptography. And I believe that understanding it on a deeper level helps to probably understand 60% of the cryptography architecture. So step number one, creating private public key pair. I mean, there are several ways to do it, and you can learn it in my article, or you can go and search and learn how to can create private public key pair. But in our case, we will be using the elliptic library, which you can install through using npm package. It's easy installation. And we also installed crypto.js, which also you can search and find it, or if you cannot find it, you can have links below the video, or you can ask me anytime. So I do assume that you have installed these two packages. And if you go deep into read API documentation, you understand that you require and you create this new ES class. We're not going to understand the algorithms here. I assume that you are familiar a little bit. If not, again, ask me questions. So after we have these libraries installed, we create a class sender. We use ES6 syntax here, which is relatively straightforward. So all the class sender does is creates a private public key pair using ES library. As you can see on the constructor, we use EC class from this library, and use the method generate key pair, and then we choose a public key again using you have to read API of elliptic library here. If you go below and read, you understand how everything is created. So it's relatively straightforward. You create public key pair, you choose a public key, and you implement digital signature. So again, to digitally sign a message, it's like step number two. you have to use some sort of algorithm, and you have to use your private key. It is extremely important that private key is yours. Anyone who has access to your private key is basically has your identity. So when it's like your fingerprint, it's like your DNA or something in a cryptography. So only sender can assign a message, and he uses essentially access to his private key to sign it. And we implement this method in our class sender. We can say that it's the rudimentary implementation of crypto wallet, but we call it class sender. I only want to note here that due to the way like elliptic library works, the message, the signed message, you have to use array. It assumes that you will provide as an input array. It probably goes from the way that you can have several separate messages to sign, but if you have only one message, please remember that you still have to use array. So now that we have our class sender implemented, and again, what does class sender does is basically we went through step one. We created private key and associated public key, and we used private key to digitally sign a message. So now we are going to the step number three, which is basically verifying the digital signature, and this is where magic is happening. So for that, we create a separate class called receiver, and it's also very simple ES6 class where you use constructor, and we accept public key, again, public key available to everyone, digital signature, and digital signature is also available to everyone, but only the person, only the sender, and remember we implemented it here, only the sender can create this digital signature using his private key. Any sender can create a digital signature, but his digital signature is correlates actually one-to-one relationship with his private key and the message itself. So after accepting all these three publicly available inputs, receiver get them and uses this verify signature method to verify if this message was really signed by the owner of private key which associated with this public key. This is aha moment, so to speak, but it's relatively straightforward if you see it in code. So once again, we create class sender, which creates private and public key, and had the ability to digitally sign the message using this sender's private key. And we also created the class receiver, the receiver which accepts public key, digital signature, and message, and uses algorithm which is implemented for us by elliptic library to verify signature. So what we want to check, the magic, what is really happening is to see if this architecture with sender and receiver works. So what does it mean? In a code, it's relatively simple. So let's assume that we have this message, and it is a payment information. So basically, let's assume that sender wants to send some bitcoins or any other funds or information to a particular person or want to reveal something. So once again, we use this message, and see we put it into square brackets because that's requirements of elliptic library. Once again, if you forget to do it, it will throw error and you will spend some time looking for it. And now what we do, it's a relatively straightforward check. We create two senders. So we create sender, which we call using new keyword, and using our class, which is sender. So we create a sender, and we create a sender one, which is two different instances of the same class, and each of these senders, sender 1 and sender 2, by definition has his own unique private public key pair. So every sender can is what he's doing. He sends into while he's a public key, and we have this public key available. So we take this public key 1 from sender 1, and we create a public key which is a sender public key. So we have two public keys, and what we just want to check that the receiver can understand who actually digitally signed a message. So basically what we do, for example, that's the most interesting thing, and just wait a second, we check it in the code again. So digital signature sender, in a way that this sender, right, uses this method digital signature and signed the message, right? So this message signed with a private key belonging to a sender. So now receiver, we create this new receiver class. We assume there is one receiver. He wants to check if this message was actually signed by sender or sender 1. So he takes in public key, digital signature, and we know the digital signature, it's interesting here that digital signature was created by sender. So it's signed by sender using his public key, which is public key. So we assume that if the receiver received public key, and public key here it's from sender, digital signature is signed by sender, which is the sender, and the message is payment information. So in this case, let's assume, so now if new receiver checks if this digital signature of this message belongs to this public key, he uses verify signature. We are going to our code right now and see what will be the result. So the result will be here. We need to check is that if we run verify signature, but you see, what I've done here is that I synchronize the code to the same code that you saw in the article. So now if new receiver receives everything like before, we should expect to see true. Why? It is clear that the receiver receives public key, digital signature message, which actually corresponds to the sender. But what will happen if he will try to check if the same message was if it belongs to the sender 1? We just save it and check, and in theory that magic happens, and now that we have a digital signature. The digital signature is created by sender, so it corresponds to public key, not a public key 1. A message is the same, but digital signature the message is signed by sender, not by sender 1, not by imposter. So we should expect, if we run false. Isn't that a magic? I understand that may look a little bit relatively simple, but what we just did, we confirmed that by using this library, elliptic library, we were able to check if it really works, if private public key cryptography really works. I have one small note here, as you may note it here, and you can ask questions, those of you that I actually used SHA-256 hashing function to hash the message, well, it's not required per se. You can obviously hash any message you want, but in practice, in Bitcoin, in any cryptography implementation, in practice, you actually do not sign a message, but you sign SHA-256 hash of message. And it doesn't change the logic, but it make it more efficient and create more security. So that's it. That's in several lines of code we will be able to implement and understand, hopefully, the private public key implementation. Please feel free to ask questions.